This is our very last chemistry lecture of the year, so we're going to get the really abridged version of VSEPR theory. VSEPR is a way of predicting the shapes of molecules. Some molecules are linear, some are bent at angles, some are triangles, whatever. So how do we figure that out? Well, VSEPR stands for valence shell electron pair repulsion. So what does that mean? We're working in the valence shell, the outermost shell of electrons. That's where all the action happens anyway, right? The core electrons are just buried. Electron pair, because electrons occur in pairs. They pair up, we put our dots together. And repulsion, that's the key here. Those electron pairs all repel each other. And so they're going to push apart as far as they possibly can get to opposite sides of the atom. So that's really all VSEPR is. Count up your electron pairs on the central atom, and then push them as far apart as you can physically get them in space. So the rest of this is just looking at what shapes you get when you do that. So I'm going to draw. Let's start with a situation where you only have two pairs. Now, I should say to clarify things here. When we talk about electron pairs, it's really kind of incorrectly named because any grouping of electrons counts as a pair. A lone pair counts as a pair, obviously. A single bond counts as a pair, which again it is, but a double bond also counts as a pair. Yeah, I know there's actually 4 electrons in there, but for VSEPR purposes, it still counts as a pair. So, for example, if I have the compound beryllium hydride, which we built when we did the incomplete octets, it has an incomplete octet. Beryllium in the middle has 1 pair, 2 pairs, that's it. Okay? But also the molecule carbon dioxide, which, again, we built this a while back. There's double bonds there. Now, in reality, of course, 2, 4, 6, 8 electrons on carbon. So you think 1, 2, 3, 4 pairs. Normally that's correct. Normally that makes sense. But for the purposes of VSEPR, each double bond counts as only a single thing. Okay? If they had asked me about this, I would have said to call it valence shell electron group repulsion, because it's not necessarily a pair, it's a grouping. A single bond is a grouping, which really is a pair. A double bond is also a grouping. So you got 1, 2 groupings on the carbon. So in this situation, notice you got 2 groupings, or 2 pairs, if you will. How they want to get as far apart as they can possibly get. Now notice I drew them linear like this, but Lewis doesn't care. Lewis wouldn't have worried at all if I had drawn it like this. When you draw Lewis structures, Lewis doesn't care about the shape of the molecule. He simply cares who's bonded to who, to whom. So we want to worry about the shape. So we've decided with these 2 molecules we have 2 pairs. So here's my central atom, whatever it is. It was a carbon, it was a beryllium, whatever. Now, if I have 1 pair right here, I can put it wherever I want because it's just going wherever. Now, if I'm going to put a second pair in there, that second pair has to repel as much as is going to repel this pair and get as far apart as possible. So if I put that second pair here, well, look how close they are. They're going to be pushing each other apart and repelling, which means that second pair is going to get pushed all the way around until it's over here. Now, could it get pushed further down to here? Well, no, because now it's getting closer again, right? So, net result is the furthest you can get away when you have 2 pairs, the furthest you can get away is being on opposite sides. It's like if you walk into a room and there's someone repulsive like Sebastian in there. He's on one side of the room. You're going to go stand on the totally opposite side of the room to get away from that repulsion, right? I'm sorry, Sebastian had to do that one last time. Same thing here. The first electron pair is right here. The second electron pair goes all the way on the other side, which means, well, look at the bond angle you get here. You get a 180-degree angle. And we say, now, we got 2 chemicals, 2 elements attached onto there, call it chemical X. Notice the bonds form a straight line. So we say that the molecule is linear. Okay? So if you have two pairs, the molecule is linear. Now, let me clear this. And by the way, so both those molecules, carbon dioxide and beryllium hydride, were both linear molecules with 180-degree angles. What if you have three pairs? There's the chemical in the middle. I'm going to put the first pair up here. Now, the second and third pair are going to also repel each other. How far can they get from each other? Well, they can space equally around chemical A, right? Which gives you in here bond angles of 120, 120, and 120, adds up to 360. So, in this case, they arrange themselves in a flat triangle, you'll see. So if I add a substance, an element onto each one of those, you'll notice the molecule forms a flat triangle. Okay? The term we use for that is trigonal planar. Makes it sound more impressive than just saying it's a triangle. Okay? So the molecule is trigonal planar shaped. Now, what if you have a lone pair? Like this chemical X up here, what if it wasn't there? It was just a lone pair of electrons. Well, then you can't see that. You can't see electrons. Now all you're left with is a molecule that's bent at an angle. So an angular molecule. A couple of examples of that. Let's look at the nitrate ion, NO3, negative charge. I'm going to draw these quickly because we've done these Lewis structures before. Nitrate ends up having this Lewis structure. And yes, there should be dots on all the oxygens, saving time here and not doing that. But you'll notice nitrogen has 1, 2, 3 pairs around it. Okay? So that means the molecule is going to be trigonal planar, a flat triangle shape. So the nitrate polyatomic ion actually forms a flat triangle with the N in the middle and the O's arranged around it like forming a triangle. You see how it makes a triangle there, right? Now, let me try another one. The sulfur dioxide molecule, SO2. If you do a Lewis structure for that, you get this. And again, there's lone pairs on the oxygens that I'm not going to waste time drawing. But notice the central atom has 1, 2, 3 pairs. A pair, again, is a lone pair is a pair, a single bond is a pair, a double bond is a pair, a triple bond is a pair. Even those odd electron molecules, the single electron counts as a pair. Any little electron grouping counts. So this has 3 pairs on it. But notice now, if I draw it, you got your sulfur, a pair, an oxygen, and an oxygen. You'll notice the 3 pairs do form a flat triangle, but you don't see the lone pair. You just see the atoms. So you got oxygen, sulfur, oxygen attached to each other at an angle. So we call this molecule bent. And the bond angle in there is 120 degrees. So, if you have 2 pairs, your molecule is going to be linear, 180-degree angle. If you have 3 pairs, well, now it depends if you have a lone pair. If there's no lone pair, it's going to be trigonal planar. If there is a lone pair, it's going to be angular. And either way, the bond angle is 120. Now, finally, we won't do expanded octets here, so we'll just do normal stuff. What if you have 4 pairs? Okay, so you got your chemical in the middle. Your Lewis structure would look like this. And you're going to be tempted to think, well, that's as far apart as they can get. 90 degrees, flat triangle, or flat square, right? But you're forgetting there's a third dimension. You could take one of these, let's say this one, and kick it out in front of the computer screen. And then kick this other one over here back behind the computer screen. And that will allow them all to spread out a little further. Okay? And the result you get is something called a tetrahedron. Now, I'm going to try to be artistic here. Now, that's a tetrahedron. It's a pyramid. So this triangle down here is the base of the pyramid. And then you got a face here, and a face back behind it. Okay? So it's a triangular pyramid. The pyramids in Egypt are square-based. Okay? This type has a triangular base. And in fact, it's very special in that every single face is an equilateral triangle. So the base is an equilateral triangle. This face on the side is equilateral. You're seeing it at an angle, so it's hard to tell. This face here is equilateral, and the one behind is equilateral. Which means it doesn't matter how you turn it. If I turn it and flip it on its side, it still looks exactly the same. For you Dungeons & Dragons nerds out there, it's a 4-sided die that you use to roll magic missile damage. Not that I've ever played. So it looks like that. Now, your atom in the middle is actually in the middle of the pyramid. And then the electron pairs, well, there's one points to the top of the pyramid. There's one pointing to the side of the pyramid. Here's one kind of coming out at you. I'll draw it as a little wedge to give it a 3D effect. And there's one going back behind. Okay? So you get your central atom in the middle of the pyramid. The tetrahedron is called. And then all the other atoms attached at the corners of the tetrahedron. Okay? Anytime you have a structure like this, for example, CH4, carbon with 4 hydrogens around it, that ends up being a tetrahedron like this. Now, what if one of them's a lone pair? Okay? So, for example, if you have the ammonia molecule, it looks like this. So you got your tetrahedron, a terrible tetrahedron, with N in the middle, bonded to a hydrogen, bonded to a hydrogen, bonded to a hydrogen. Notice again, 1, 2, 3, 4 pairs. That's why I'm drawing a tetrahedron. But that fourth pair up there is a lone pair. And you don't see that. So what you have here now is a flattened pyramid. You got nitrogen bonded to hydrogens in a flattened pyramid shape with the top of it chopped off because now it's just a lone pair that you can't see. So it's kind of still like a tetrahedron, but it's now squished. We call this, well, a triangular pyramid, or more technically, a trigonal pyramid shape. Okay? So this type of molecule is trigonal pyramidal shaped. It's a squished pyramid. Okay? So if you have 4 pairs, you got a tetrahedron. All 4 of them are used, there's your tetrahedron. If one of them's a lone pair and only 3 of them are used, then the shape is trigonal pyramidal. Finally, what if 2 of them are lone pairs? The H2O molecule looks like that. Well, again, there's 1, 2, 3, 4 pairs. So you got yourself a tetrahedron. Oxygen in the middle, bonds to hydrogen, bonds to hydrogen. That side's a lone pair, the other side's a lone pair. Notice your molecule now is O with H's attached, bent at an angle. So again, we're down to an angular molecule. If I pull that out, I got O, H, H. The difference here between this and the other one that I looked at before is the bond angle inside here is not a triangle angle. It's not 120 degrees anymore. Okay? The angle inside of a tetrahedron, this angle in here, this one in here, any of these angles up here. Okay? The angle inside of a tetrahedron is 109.5 degrees. Okay? So in this molecule, which I said was CH4, if I did it for real, this is a 109.5 degree angle. In ammonia, 109.5 roughly. In a water molecule, 109.5 degree angle. Now, in the real world, they deviate slightly from that. If you actually measure the water molecule's angle, you find it's like 104.8 degrees. It's slightly less than this for reasons you'll talk about when you take more advanced chemistry courses. But that is now your last chemistry lesson ever. I'll give you a little list of all these to help you summarize it, and then what you'll do is you'll take the Lewis structures you did last night and figure out what their shapes must be based on now knowing this VSEPR stuff. And that's it.